Reed Wiseman was floating 252,756 miles from Earth when he saw the first one. A flash. Sharp. Bright. Gone in less than a second. On the surface of the moon directly below him. Then another one. Then another. By the time the hour was up, he and his crew had watched the moon get hit 6 times. 6 rocks from deep space detonating on a world with no atmosphere, no shield, no warning system of any kind, and nobody on Earth could reach them to talk about it because for 40 minutes during this exact window, the moon itself was blocking every radio signal between the Orion spacecraft and the rest of humanity. 4 people, floating behind the moon, watching it explode, in complete silence. Now here is the part that should genuinely bother you. NASA's ground-based telescopes have been watching the moon since 2006, 20 years of patient, careful observation. And in those 20 years, they average about 20 detectable impact flashes per year. 20 per year. Wiseman's crew saw 6 in 1 hour, so either something extraordinary happened on April 6, 2026, or we have been watching the moon from the wrong place for 400 years and completely misunderstanding what is actually happening on its surface. And everything we are now planning to build up there, the habitats, the outposts, the permanent human presence, is being designed around a picture of the moon that may be dangerously incomplete. Stay with me. Because this goes much deeper than impact flashes. By the time we get to the end of this, you are going to see the moon differently. Not just what the Artemis II crew witnessed out there, but what it means for every mission that follows, what it means for the people who are going to live there, and why one moment during this mission that had nothing to do with science stopped mission control in Houston completely cold. Let me take you back to April 6th. Let me put you in that capsule. The Orion spacecraft, which NASA named Integrity for this mission, had been in transit for 4 days. The crew was Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen. Between the 4 of them, they represented more human firsts than any crew in the history of deep space flight. Koch was the first woman to travel beyond Earth orbit. Glover was the first black astronaut on a lunar mission. Hansen was the first non-American to fly to the moon, and Wiseman was flying this mission after years of raising his 2 daughters alone following the death of his wife Carol in 2020. But none of that was what they were thinking about at 8:35 p.m. Eastern on April 6th. At that exact moment, the sun was disappearing behind the moon. From where they were floating, roughly 4,000 miles above the lunar surface, the entire disk of the moon went dark. It just hung there in front of them, a perfect circle of nothing, rimmed by the ghostly white glow of the solar corona, spreading outward into space like a crown of white fire. And Wiseman reached for his microphone. He said, and I want you to hear these words carefully because this is a trained test pilot who has spent years learning to keep his voice flat and professional under pressure. In the pressure, it is indescribable. No matter how long we look at this, our brains are not processing this image in front of us. It is absolutely spectacular, surreal. There are no adjectives. I need to invent some new ones. Victor Glover followed him. Humans probably have not evolved to see what we are seeing. Jeremy Hansen, looking at the corona streamers extending outward into the blackness like delicate threads of light, compared them to baby hairs, fine, luminous filaments radiating away from the blocked sun in every direction. And then Glover found the metaphor that captured it. He said if you have ever seen the spotlight off the top of the Luxor Hotel in Las Vegas at night, the beam that shoots straight up and is visible from 40 miles away, this looked like what that spotlight wants to be when it grows up. The solar corona made a 42 billion candle power beam look like a flashlight. This eclipse lasted 57 minutes, not 2 minutes like the ones you watch from a field on Earth while people around you cry and cheer. 57 minutes, nearly an hour of the sun's disk completely blocked, the corona fully visible. The crew floating in the shadow of the moon with their eyes adapted to the darkness, and nothing between them and that light except vacuum. And it was during this window while the eclipse was happening and the near side of the moon was as dark as it ever gets, lit only by the faint reflected glow of Earth itself bouncing back off the lunar surface, that the flashes started. Let me explain exactly what they were seeing and why the conditions that night created something that had never existed before in the history of human observation. When a meteoroid hits the moon, it arrives at speeds between roughly 20 and 70 kilometers per second. put that number somewhere you can feel it. 70 kilometers per second is over 156,000 miles per hour. At that speed, you could cross the entire United States in under a minute. You could circle Earth in about 10 minutes. When something moving that fast, it's solid rock. It does not bounce. It does not slow down. It stops in microseconds across a distance measured in millimeters. Every single joule of kinetic energy converts instantaneously into heat, pressure, and light. The meteoroid vaporizes, not melts, vaporizes, goes directly from solid to superheated plasma in a time frame so short that the word instant does not capture it. The rock around the impact point vaporizes too. A shock wave radiates outward into the regolith faster than sound travels through rock, which is itself several kilometers per second, and that shock wave excavates a crater not over hours or days, but in milliseconds. Material is ejected outward in every direction. On the moon, there is no air to slow it down, so it travels for hundreds of kilometers before landing. At the center of all of this, for a fraction of a second, there is a flash. Material heated to tens of thousands of degrees, glowing brilliantly across the visible spectrum before going dark. That is what Wiseman saw. Now here is what made that night different from every other night in history. Normally, when we try to watch for these flashes from Earth, we are doing it from 239,000 miles away, through 100 kilometers of turbulent atmosphere that blurs, scatters, and dims the signal. We can only watch during specific lunar phases when the dark side of the moon is facing us. We need clear skies. We need the moon above the horizon at a reasonable angle. We need the faint flash to survive its quarter-million-mile journey through all that atmosphere and still be bright enough to register on a detector. Stack all those constraints together and you end up watching the moon through what amounts to a very long, very dirty tube. And the faintest signals, the ones from smaller impacts that still carry enormous energy but do not produce quite enough light, they simply vanish. They existed. They happened. The moon was struck, but the atmosphere absorbed the evidence before it could reach the detector. Wiseman's crew had none of those constraints. They were 4,000 miles from the surface instead of 239,000. There was no atmosphere between their eyes and the moon. The solar eclipse geometry had darkened the entire near side of the moon in a way that maximized contrast between any flash and the background. The Earthshine provided just enough ambient light to see surface features, but not enough to wash out anything bright. And 4 sets of trained human eyes, plus multiple camera systems, were watching a fully dark hemisphere with nothing between them and a vacuum. If you sat down with a blank piece of paper and tried to design the most sensitive possible impact flash detection system that has ever existed, you would design almost exactly what the Artemis crew had by accident. Every single variable that normally degrades the signal was simultaneously absent. Every factor that normally inflates the noise was removed. And in that 1-hour window of conditions that had never existed before, they saw 6 flashes. Now I want to be precise here, because the comment sections on videos like this are full of people doing math that sounds alarming but is actually wrong. So let me walk you through why the comparison between 6 per hour and 20 per year is not a simple multiplication problem, and why what it actually tells us is more important than any made-up annual rate. If you just multiply 6 per hour by the number of hours in a year, you get something like 52,000 flashes per year, and some people will say that is 2,000 times NASA's reported rate, which proves the moon is far more dangerous than we thought. That number is wrong, probably by a significant margin. Here is why. The Artemis crew was not observing the moon under average conditions. They were observing it under the most favorable conditions that have ever existed. The eclipse geometry meant they could detect flashes far fainter than what any standard observation, even from orbit, would normally catch. They were sampling deeper into the size distribution, detecting smaller impacts that would be invisible to everything else we've ever pointed at the moon. The window may also have coincided with the moon passing through a minor meteoroid stream, a temporary ribbon of cometary debris that temporarily elevates impact rates above their long-term average. So that 52,000 figure is almost certainly an overestimate. But here is the thing. Here is what actually matters. Even if you discount it by a factor of 10, even if you assume that 90% of what they saw was enhanced by those exceptional conditions, you still end up with an impact detection rate that is orders of magnitude above 20 per year, not twice as high, not 10 times as high, orders of magnitude. And the planetary scientists who study this for a living are not surprised by that. The theoretical models have been saying this for decades. The calculations built on orbital particle detector data, crater size distributions, and analysis of returned Apollo samples have long pointed toward a true impact rate, far higher than any ground-based program could confirm. We just never had the visual confirmation. The "I watched it happen" confirmation that makes something feel real in a way numbers on a page never quite do. The Artemis crew provided that confirmation. What they saw was not an anomaly. It was not evidence that something unusual happened on April 6th. It was the model confirmed visually for the first time in history. The theory predicted this. The observation matched. The gap was never between prediction and reality. The gap was between reality and what we could see from Earth, and that gap has massive consequences for what we are about to build on that surface. Here's a question I want you to sit with for a second before I answer it. Drop it in the comments if you want to think through it yourself. If NASA's ground-based system only detects the brightest flashes, the ones from larger impactors, and the Artemis crew with their perfect conditions could see much fainter ones too, what does the full size distribution actually look like? And how many impacts in the size range that really matters for habitat engineering are happening that we have never been able to count? I will come back to that, but first let me tell you about the 40 minutes of silence, because that is its own story. At 6:44 p.m. Eastern Time on April 6, 2026, Orion slipped behind the moon. One moment, NASA's Deep Space Network, the chain of massive antenna stations in California, Spain, and Australia, was tracking the crew in real time, receiving telemetry, monitoring life support, hearing their voices. The next moment, silence. The moon's mass blocked every radio signal, every data stream, every link between the crew of Artemis II and the rest of humanity. The screens in mission control at Johnson Space Center in Houston went dark. Flight Director Judd Freeling had warned everyone this was coming. He had told his team that physics would take over and that physics would absolutely get them back to the front side of the moon. But physics does not talk back, and for 40 minutes nobody on Earth could do anything at all except wait. The crew had been briefed on this. They had trained for it. Intellectually, they understood it was coming, but there is a difference between understanding something and experiencing it with your body. What they felt during those 40 minutes was not the kind of isolation you get when you drive into a dead zone on a country road and lose your cell signal. This was absolute. There was no backup channel, no emergency frequency, no one to call. 4 human beings, sealed inside a capsule the size of a large SUV, floating in the void behind the moon, with no line of sight to Earth, no line of sight to Earth, no line of sight to any satellite, no line of sight to any other living person on the planet. They were on their own in the truest possible sense of that phrase, and while they were cut off, they watched Earth disappear. It is called Earth's set. As Orion swung behind the far side, the crew watched their home planet drop below the lunar horizon and vanish. One moment Earth was there, bright and blue hanging in the black. The next it was gone, hidden behind 4,000 miles of lunar rock. Christina Koch spoke about it afterward. She said one of the biggest highlights of the entire trip was coming back from the far side and having the first glimpses of planet Earth again after being out of contact for about 45 minutes. It really just reminded her what a special place they have. Notice what she chose to talk about. Not the science, not the observations. She talked about seeing Earth again. The absence of Earth was not just visual, it was psychological. It was something closer to existential. During the blackout, the crew kept working. They photographed and described far-side terrain. They watched for impact flashes. Hansen reported seeing 2 of them during those 40 minutes, 2 explosions on the moon while cut off from every other member of the human species. They also celebrated briefly, in the way that astronauts celebrate, which is to say they shared maple cream cookies that Hansen had brought from Canada, floating in microgravity behind the moon, eating cookies while rocks detonated on the surface beneath them. Wiseman called it surreal. I imagine that is something of an understatement. When Orion came around at 7:24 p.m. and the 24 b.m. and the Deep Space Network reacquired the signal, the crew broke their record. At 7:07 p.m., still behind the moon and still in complete blackout, they had reached their maximum distance from Earth, 252,752.52 license 76 miles. Farther than any human being has ever been from home. They broke the record in silence. No cheering from mission control, no live broadcast, No one watching, just 4 people and the math. Now I want to talk about what they actually saw on the far side, because this is one of the things the crew described that has not gotten nearly enough attention. Every photograph you have ever seen of the moon, every familiar image of that grey pockmarked surface shows you the near side, the side that faces Earth. And thanks to the fact that the moon is tidally locked, rotating at exactly the same rate it orbits us, you have only ever seen that one face from the ground. The far side was completely invisible to humanity until 1959, when the Soviet Lunar 3 probe sent back the first blurry photographs. What the Artemis II crew saw when they came around was something fundamentally different. Koch was the first to describe it. She said, "The more I look at the moon, the browner and browner it looks." The crew reported shades of brown, hints of blue, greenish hues in the highland regions, color variations that no satellite image had captured in quite this way. They compared notes during observation shifts and found that different crew members were perceiving different things depending on their angle and the changing sunlight. This was exactly what NASA's science team needed. Human eyes processing nuance in real time that fixed cameras cannot replicate. But the most striking thing about the far side was not the colors, it was the absence. On the near side of the moon, roughly 31% of the surface is covered in dark volcanic plains called Maria, the ancient lava flows that give the moon its familiar face. The Sea of Tranquility, where Apollo 11 landed. The Sea of Serenity. Those dark, smooth basalt sheets were created by volcanic activity billions of years ago. The far side has almost none of this, less than 1% Maria coverage. Instead, it is an unbroken expanse of ancient battered highland terrain. Craters on top of craters on top of craters stretching to every horizon. A surface that has been hammered for 4.5 billion years without the volcanic resurfacing that smoothed out the near side. And the reason for this asymmetry runs deep. The far side crust is up to 20 kilometers thicker than the near side crust. When asteroids slammed into the far side and cracked it, the magma below could not easily reach the surface. The cracks did not go deep enough. The lava stayed underground. On the near side, the thinner crust cracked all the way through and molten rock flooded the basins. But why is one side thicker than the other? A 2025 study published in Nature confirmed what scientists had long suspected. The near side of the moon contains a geological region called the Procellarum Curie terrane, Curie standing for potassium, rare earth elements, and phosphorus. This region is enriched in radioactive elements, uranium, thorium, potassium, that generate heat as they decay. For billions of years, this radioactive engine drove volcanic activity on the near side, kept the interior warm, powered the eruptions that created those dark plains. The far side got none of it. The far side ran cold, and in September 2025, analysis of samples returned by China's Chang'e 6 mission, the first samples ever collected from the lunar far side, confirmed this temperature difference in extraordinary detail. The far side lavas that did manage to reach the surface formed at roughly 1800 degrees Celsius, about 100 degrees cooler than near-side basalts. Professor Yang Lu of University College London called it the two-faced moon. One side ran hot and volcanic, the other stayed cold and barren. The chemical lottery that decided this happened in the first few million years of the moon's existence, possibly during its earliest molten phase when radioactive elements concentrated on one hemisphere through a combination of tidal interactions with the early Earth and asymmetric cooling patterns. One side got the uranium and the thorium, the other did not. And from that moment forward, the moon's entire geological destiny was written. The crew of Artemis II was looking at the result of that coin flip, a surface that reflects 4.5 billion years of uninterrupted bombardment with nothing to erase it. No weather, no plate tectonics, no volcanic resurfacing, just craters accumulating in silence for longer than complex life has existed on Earth. The Chang'e 6 samples revealed something else that matters enormously for the future. The far side samples contained less than 2 micrograms of water per gram of rock. The near side can contain up to 200 micrograms per gram. The far side of the moon is, for all practical purposes, bone dry. If you are planning to build a permanent human presence on the moon, you need water. Not just for drinking, for growing food, for manufacturing rocket propellant by splitting water molecules into hydrogen and oxygen through electrolysis, Without water, you are entirely dependent on resupply from Earth, which is enormously expensive and operationally fragile. This is why the lunar South Pole has become the target for the next generation of missions. Certain craters near the poles are in near-permanent shadow, cold enough to have trapped and preserved water ice delivered by comets and asteroids over billions of years. Multiple spacecraft have detected signatures consistent with water ice in these permanently shadowed craters. If it is there in usable quantities, it changes the economics of lunar exploration completely. And it was near the lunar South Pole that at least one of those impact flashes appeared during the Artemis II flyby. I want to pause on that for a moment, because that is not just a data point. That is a direct challenge to a set of assumptions that are currently driving billions of dollars of mission planning. The South Polar region is exactly where NASA, ESA, JAXA, and multiple international partners plan to establish the first long-duration human presence beyond low Earth orbit. Artemis III, the first crewed lunar landing since Apollo 17, is designed to put astronauts near the South Pole. The Lunar Gateway orbital station will support surface operations in that region. The long-term vision includes permanent habitats, resource extraction facilities, scientific outposts, all of it planned for the pole. And while mission planners were working on those plans, a rot from deep space detonated near those exact coordinates while 4 astronauts watched from orbit. The physics of the polar impact environment do offer some modest comfort. The geometry of polar latitudes, the way impactors approach at shallower angles, combined with specific velocity distributions, produces a slightly lower flux rate in polar regions compared to the equatorial belt. But slightly lower than continuous bombardment is still continuous bombardment, and a modest discount on the price of living under a meteoroid storm is still a very high price. Let me now get specific about what that price actually looks like in engineering terms, because this is where the Artemis II observation becomes most consequential and where I think most coverage has significantly underplayed the implications. When people talk about meteoroid risk on the Moon, they tend to focus on the dramatic end of the size distribution. The rocks large enough to produce visible flashes, the impactors that excavate craters meters wide. These are real. They are the things Wiseman's crew watched happen, but in terms of actual engineering threat to a habitat, they represent only the thinnest sliver of the total flux. Beneath those visible impactors in the size distribution is a population of particles so numerous and so small that they are individually invisible but collectively relentless. These are micrometeoroids. Particles typically smaller than a millimeter across, sometimes smaller than a human hair. But they move at the same hypervelocity speeds as their larger cousins, because in the interplanetary environment, speed is governed by orbital mechanics, not by mass. A particle the width of a dust grain traveling at 20 kilometers per second carries kinetic energy wildly disproportionate to its size. A recent study estimated that a lunar surface structure with an exposed area comparable to the International Space Station would be struck by between 15,000 and 23,000 of these particles every single year. Let me make sure that lands properly. Not a single dramatic event to plan around. 23,000 impacts per year on a single structure. That is continuous, invisible, permanent erosion, a sandblasting that never stops, operating at every scale simultaneously, degrading surfaces, pitting optical coatings, weakening structural materials, accumulating damage over time in ways that are individually undetectable and collectively catastrophic over long time scales. We have direct physical evidence of what this looks like in practice. From 2.5 decades of operating the International Space Station, the exterior surfaces of ISS modules after all those years in low Earth orbit show thousands of micrometeoroid impact craters visible to the naked eye during spacewalks. Some of those craters are centimeters wide, large enough to be genuinely alarming when you are floating next to them in a suit. Cupola windows have been chipped and pitted by particles estimated to be only a few thousandths of a millimeter across. Handrails used by spacewalking astronauts show erosion from years of hypervelocity exposure. And the ISS has it relatively easy. It benefits from Earth's magnetic field, which deflects a significant fraction of the charged particle flux that would otherwise add to the erosion burden. It operates in low Earth orbit where the meteoroid environment, while present, is less intense than the interplanetary environment the Moon inhabits. On the Moon, there is no magnetic field assistance. The meteoroid flux is higher. The exposure would be continuous and unrelenting. the cumulative damage over equivalent time periods would be substantially worse. The standard engineering response to this is something called a Whipple shield, named after astronomer Fred Whipple, who first described the concept in the 1940s. The idea is elegant. Instead of building one thick wall and trying to make it strong enough to stop incoming particles directly, you build two or more thin walls separated by a gap. When a hypervelocity particle hits the outer bumper layer, it punches through, but in doing so, both the particle and the wall material shatter and vaporize. The single concentrated projectile becomes an expanding cloud of slower, more diffuse debris. By the time that cloud reaches the inner pressure wall, the energy has been distributed over a much wider area at lower effective velocity, and the inner wall can absorb it without being penetrated. Modern Whipple shields are extraordinarily well designed. Contemporary versions use multiple intermediate layers of specialized materials, ceramic fabrics, metallic meshes, combinations of high-strength polymer films. They can intercept an estimated 99.999297% of incoming particles at design velocities and angles. But 99.999297% is not 100%, and the mathematics of long-duration exposure are unforgiving. The remaining 0.00% applied to 23,000 impacts per year still means roughly one particle in every 3 million gets through. Over 10 years, that is a statistically meaningful number of penetration events. Over 20 years, it is a design parameter that has to be actively managed through redundant pressure vessels, rapid leak detection systems, and emergency patching protocols that crews would have to execute in spacesuits while exposed to the same environment that caused the problem in the first place. Whipple shields also scale badly as habitats grow. A habitat complex designed to house a crew of 12 with full life support redundancy and scientific laboratories might have 10 or 20 times the exterior surface area of a single ISS module. That means 10 or 20 times the annual impact count, which means 10 or 20 times the shielding area to maintain, inspect, and eventually repair or replace. The mass penalty compounds in ways that become prohibitive at the scales needed for permanent settlement. This is why many engineers thinking seriously about long-term lunar habitation have concluded that the only solution with genuine viability is not a shield designed in a laboratory and shipped to the CA. Moon. It is a shield the moon itself already provides in unlimited quantities. Regolith, the loose, fragmented, pulverized rock and dust that blankets the lunar surface to depths of several meters, itself the product of 4 billion years of the same bombardment we are discussing, is an extraordinarily effective absorber of kinetic energy. Put 2 to 3 meters of regolith on top of a habitat structure, and you have a shielding layer whose mass density no manufactured material can match at any reasonable cost. A particle that would punch straight through a Whipple shield at full speed encounters meters of granular material that progressively absorb, scatter, and ultimately stop it long before it reaches any pressurized wall. Regolith shielding also addresses cosmic radiation, the high-energy particles streaming continuously through the interplanetary environment from supernovae and galactic sources, which pose serious long-term health risks to anyone living on the lunar surface for extended periods. The same 2 to 3 meters of regolith that stops micrometeoroids provides substantial radiation shielding. Two critical problems addressed by one architectural decision. The catch is that the excavation and construction challenges are genuinely enormous. Moving the hundreds or thousands of tons of regolith needed to cover a meaningful habitat requires heavy equipment, excavators and haulers and graters, that does not currently exist in flight-qualified form, has never been tested in the lunar environment, and would itself need to be landed on the moon before any construction could begin. Building pressure-sealed structures with sufficient structural integrity to bear the weight of continuous regolith overburden without settling or cracking over decades requires engineering approaches well beyond anything currently in the prototype pipeline. The entire approach depends on in-situ resource utilization at a scale that has never been demonstrated anywhere but a laboratory, and it transforms every subsequent design question. How do you provide natural light to the inhabitants of a bunker? How do you ventilate it, expand it, maintain its exterior, conduct emergency egress? None of these challenges are insurmountable. They are engineering problems, not physics problems. They can be solved given sufficient resources and sufficient time, but they can only be solved well if the inputs going into the engineering, starting with the actual meteoroid flux the habitat will experience, are accurate. And this is exactly where the Artemis II observation becomes most consequential. If our best flux estimates had been built on ground-based detection data that was systematically filtering out most of what was happening, then the safety margins being designed into lunar habitats may be thinner than the people building them believe. Not because the engineers are careless, because the observational foundation they're working from has a blind spot at its center. The visible flashes Wiseman's crew saw were the tip of the iceberg. The unseen micrometeoroid flux is the vast mass beneath the waterline, and just as our ground-based telescopes could only see the brightest impacts, our engineering intuition naturally focuses on dramatic single-event failures while underweighting the slow, steady degradation that is actually more dangerous of mission timescales measured in decades. Closing that gap is not optional. It is the most urgent task in lunar surface engineering, and it requires exactly what the Artemis II crew did by accident: persistent observation from inside the cislunar environment, where none of the filters that distort our Earth-based picture of the moon apply. Drop your answer in the comments right now. If you were designing a lunar habitat, which approach would you choose first? Engineered shielding like Whipple shields that you know and can test on Earth, or regolith burial that uses the moon's own resources but requires technology we have not yet proven in space? I am genuinely curious what your instinct is and why. Now I need to tell you about something the Apollo astronauts experienced, that the Artemis II crew experienced too, and that almost nobody talks about when they cover these missions, because it is strange, and it is a direct, visible symptom of something that is silently damaging the human body in deep space. It started with Buzz Aldrin on Apollo 11. He was floating in the command module in darkness, eyes closed, trying to sleep, and he saw a flash. Not through the window, not from an instrument panel. Inside his eye, a brief streak of white light that appeared and disappeared in less than a second. He opened his eyes. The cabin was dark. Nothing had changed. He closed his eyes again. Another flash. Every subsequent Apollo crew reported the same phenomenon. Apollo 12, 13, 14, 14, 15, 16. Every astronaut who traveled beyond Earth orbit and spent time in darkness saw these flashes. They came in three varieties. Some were points, brief pinpoints of light appearing behind the eyelid. Some were slightly larger, slightly longer-lasting spots, and some were streaks, lines of light that traced across the visual field and vanished. The astronauts were not hallucinating. They were being shot. The explanation is cosmic rays, high-energy charged particles that originate from some of the most violent events in the universe. Supernovae, black holes, the shock waves of colliding galaxies. These particles are accelerated to velocities approaching the speed of light and flung across the cosmos. They travel for millions of years through unimaginable distances, and some of them end up passing through our solar system. On Earth, we are protected by two shields we never think about. The magnetosphere, generated by Earth's molten iron core, deflects the majority of incoming charged particles, and the atmosphere absorbs most of what makes it past the magnetic field. We live inside a planetary defense system we have never had to maintain or even consciously appreciate. The moon has neither. The moon has no global magnetic field. Not anymore. It once did, billions of years ago, when its interior was hot enough to sustain a dynamo similar to Earth's. But as the moon cooled and its core solidified, the dynamo died, the field collapsed, and the moon has no atmosphere worth mentioning. Its exosphere, the ghost of an atmosphere it has, contains roughly 10 metric tons of gas total. Earth's atmosphere masses 5 quadrillion metric tons. The moon's gas envelope is, for practical purposes, nothing. So out there, in the space between Earth and the moon, cosmic rays pass through everything. Through the walls of the spacecraft, through the crew's bodies, some of them through their eyes. There are 3 mechanisms that likely explain what the astronauts were seeing. The first is Cherenkov radiation. When a charged particle travels through a medium faster than the speed of light in that medium, it produces a brief flash of bluish light. Light travels slower through the vitreous humor of the eye than through vacuum. A cosmic ray particle moving near light speed can exceed the local speed of light inside the eyeball and produce a visible flash. This is the same physics that creates the eerie blue glow you see in the water surrounding nuclear reactors. The second mechanism is direct ionization of retinal cells. The particle deposits enough energy passing through the retina to trigger the photoreceptor cells, causing them to fire as if struck by actual light. The brain interprets this as a flash. The third mechanism involves direct interaction with the optic nerve or visual cortex, cosmic rays passing through the skull and interacting with the neural tissue responsible for processing vision could produce the sensation of light without ever touching the eye at all. On average, Apollo astronauts reported seeing roughly one flash every 3 minutes during dark adapted observation sessions. The flashes are not just a curiosity. They are a symptom, a visible, perceptible indication of invisible damage happening in real time. Every flash represents a cosmic ray particle passing through the astronaut's head at nearly the speed of light, depositing energy, breaking molecular bonds, and moving on. The health consequences of long-term deep space radiation exposure are not fully understood, but the early signals are concerning. Studies of Apollo astronauts have shown significantly elevated rates of cardiovascular disease compared to astronauts who never left low Earth orbit. The sample size is small. Only 24 humans have ever traveled beyond Earth orbit, and all were Apollo-era men. But the pattern is consistent with what radiation models would predict. Cosmic rays damage DNA. They cause mutations. In the brain, where neurons do not regenerate the way other cells do, damage accumulates. Studies on mice exposed to simulated galactic cosmic ray environments have shown cognitive decline, increased anxiety, and impaired memory formation. The relevance to humans over multi-year missions is still being characterized, but the implications for Mars exploration are serious in ways that go far beyond what most mission planning documents acknowledge. The Artemis II crew saw these flashes during their 10-day mission. They were warned to expect them. They experienced them, and they began the journey home carrying in their eyes the most direct possible evidence of what deep space does to the human body. Light that comes from inside, generated not by any source in the cabin or outside the window, but by the universe itself passing through them. I want to come back to something I said near the beginning about the overview effect, because I think it is undersold in coverage of missions like this, and I think it actually matters. The overview effect is a term coined by space philosopher Frank White in 1987. It describes the cognitive shift that astronauts report experiencing when they see Earth from space. Not just the feeling of awe, though awe is part of it. A more fundamental restructuring of perspective. The borders become invisible. The conflicts that consume daily life on the surface shrink to abstraction. The planet looks like what it actually is. A single system, a single organism, a single home shared by every living thing. It tends to stay with astronauts. They say they never see the world quite the same way again. Victor Glover, floating 252,000 miles from home, looked out at Earth and said, "Trust us, you look amazing, you look beautiful. You also look like one thing. Homo sapiens is all of us, no matter where you are from or what you look like, we are all one people." Jeremy Hansen said, "Right away you are humbled. The fact that 4 of us get to be out here just brings you to your knees." Christina Koch, when asked to describe the mission in one word, did not say historic. She did not say record-breaking. She said humility. And Jim Lovell, who flew to the moon on Apollo 8 in December of 1968 and was the first human to witness Earthrise from lunar orbit, recorded a message for the Artemis II crew just 2 months before his death at the age of 97 in August 2025. Mission Control beamed it up to Orion on the morning of the flyby. He said, "Hello Artemis II, this is Apollo astronaut Jim Lovell. Welcome to my old neighborhood. It is a historic day and I know how busy you will be, but do not forget to enjoy the view." Wiseman's response was quiet. "It is just a real honor to have that on board with us. Let us go have a great day." The crew was also carrying something physical from Lovell, the original Apollo 8 silk mission patch that had flown with him to the moon in 1968. They brought it aboard Orion. That patch had now traveled to the moon twice. Different hands, different decades, same journey. The connection between Apollo and Artemis is not just symbolic. Artemis II flew a free return trajectory, the same type of path as Apollo 13, using the moon's gravity to slingshot around the far side and return to Earth. The same orbital mechanics, the same physics, the same route through space that Lovell had flown when his oxygen tank exploded, and his crew spent 4 desperate days using the lunar module as a lifeboat to get home. This time the spacecraft was healthy. The crew was prepared. The mission was going exactly as planned. This time, the view was the point. Now I need to tell you about the moment that stopped Mission Control cold. It started when Jeremy Hansen took the microphone. The crew had been working through their observation targets. They were photographing and describing geological features of the lunar surface, doing exactly what the science team had asked. And then Hansen's voice shifted, still steady, still professional at first, but something underneath it had changed. He said, "A number of years ago, we started this journey, and in our close-knit astronaut family, we lost a loved one." He paused. Her name was Carol, the spouse of Reed, the mother of Katie and Ellie. Carol Taylor Wiseman was a neonatal intensive care nurse. She spent her career in hospitals caring for the smallest and most fragile human beings through their first days of life. She worked at the Children's Hospital of the King's Daughters in Norfolk, Virginia. She moved wherever her husband's career with NASA took their family. She was 46 years old when she died of cancer in 2020. Wiseman has been raising their 2 daughters alone since. While scanning the lunar surface during the flyby, the crew had identified 2 small, previously unnamed craters. On the Moon, unnamed features are common. There are more craters than anyone has ever had time to catalogue, and the International Astronomical Union has a formal process for naming them. The first crater, located near the Oriental Basin, they wanted to name Integrity, after their spacecraft, and after the foundation of trust and candor and humility that had defined their years of training together. The second crater sat on the boundary between the near and far sides of the Moon, near the Glishko crater, on the same latitude as what is known as the M crater. It was a bright spot visible from Earth at certain points during the Moon's transit across the sky, fresh enough that it still glowed against the older, darker surface around it. Hansen described its location and then said, "It is a bright spot on the Moon, and we would like to call it Carol." As he spoke, Wiseman reached over and put his hand on Hansen's shoulder. His eyes were wet. He pressed his lips together and nodded. Then they embraced. Not a formal handshake, not a profane pat on the back. A real hug, the kind that happens when grief and love and distance collapse into a single moment, 4.5 billion miles from the sun. And then Koch and Glover joined them. All 4 astronauts pulled together in a floating embrace, wiping tears, holding each other in microgravity 252,000 miles from home. Mission control in Houston went silent. The science team watched. The flight controllers watched. The families in the viewing gallery watched. Nobody spoke. The moment belonged to the crew and to a woman who was not there. Carol Wiseman did not get to see her husband launch. She did not get to watch him fly to the Moon. She did not get to hear him describe the far side, or the impact flashes, or the eclipse, or the corona wrapping around the edge of a black disk like white fire. But if the International Astronomical Union approves the name, and there is every reason to believe they will, there will be a bright spot on the Moon called Carol. Visible from Earth, a spot their daughters can find on a clear night and know their mother's name is written on another world. Someone in the comments of another video about this mission put it simply and perfectly. Her babies can look to the night sky and see their mum. I have nothing to add to that. Let me take you now to one of the most scientifically significant observations the crew made, one that almost no one is talking about, because it did not produce dramatic footage, and it did not generate an emotional moment, but it may turn out to be the most consequential piece of data from the entire mission in terms of what it tells us about the Moon's hidden structure and history. When the crew flew over a region on the near side called Rhina Gamma, they were looking at one of the most mysterious features on the entire lunar surface. Rhina Gamma is a bright, tadpole-shaped marking on a dark basalt plain. It was first spotted through telescopes in the 1600s and has been studied, debated, and puzzled over ever since. It is not a crater. It is not a lava deposit. It is a swirl, a bright curved pattern on the surface with no obvious geological origin, as if someone had painted a pale brushstroke across the dark landscape. The crew observed it from an angle and under lighting conditions that no satellite image had captured in exactly this way, and their descriptions will be analyzed for months. But the deeper mystery of Rhina Gamma is what lies beneath it. It sits directly on top of one of the strongest magnetic anomalies on the Moon. This requires some explanation, because the Moon's magnetic situation is strange. Earth has a global magnetic field generated by the churning of molten iron in its outer core. This field wraps around the planet, deflects solar wind particles, protects us from cosmic rays, and makes compasses point north. The Moon once had a similar field, Billions of years ago, its interior was hot enough to sustain a magnetic dynamo, but as the moon cooled and its core solidified, the dynamo died. The global field collapsed, except it did not disappear entirely. Scattered across the lunar surface are dozens of localized magnetic patches, small regions where the rocks retain a magnetic signature from a field that no longer exists anywhere else on the moon. These anomalies are weak compared to Earth's field. Sometimes just a few hundred nanots last against Earth's 50,000. But they are measurable, and many of the moon's bright swirls, including Rhina Gamma, sit directly on top of them. The leading theory for why is called the magnetic sunscreen hypothesis. The solar wind, the constant stream of charged particles flowing outward from the sun, hits the unprotected lunar surface and slowly darkens it through a process called space weathering. This chemical and physical alteration of surface material happens over millions of years and gradually turns the moon's surface gray. But where a localized magnetic anomaly exists, the field, even weak as it is, can deflect some of the incoming solar wind particles. The surface beneath the magnetic patch receives less bombardment, less weathering, less darkening. It stays brighter. The result is a visible marking on the surface that mirrors the shape of the underlying magnetic field beneath it. A 2018 study published in Communications Physics confirmed that the magnetic field around Rhina Gamma is the right shape and strength to produce the observed swirl pattern through exactly this mechanism. The swirl is a shadow cast not by light, but by magnetism. But where did these magnetic anomalies come from? The global field died billions of years ago. What magnetized these specific patches of rock? Three competing explanations exist. The first proposes that comet impacts deposited magnetized material. The second suggests that basin-forming asteroid impacts launched iron-rich ejecta that locked in a magnetic signature as it cooled in the presence of the moon's ancient dynamo. The third, supported by a 2024 study in the Journal of Geophysical Research Planets, suggests that high titanium magma cooling underground can produce magnetic fields strong enough to explain the observed anomalies. In this model, the magnetic patches are not surface deposits at all. They are underground magnets buried deep in the crust, projecting their fields upward through miles of lunar rock to create visible markings on the surface. A February 2026 study from Oxford helped settle a decade-long debate about the moon's magnetic history. Previous research had produced contradictory results about when the lunar dynamo operated and when it died. The Oxford team showed both sides had been partially correct. The field existed in multiple phases, operating at different intensities at different times, before finally dying out approximately 1 billion years ago. The swirls on the moon's surface are records of that complex magnetic history. Tattoos left behind by a field that no longer exists. Written in iron. Frozen in time. NASA had planned a dedicated mission called Lunar Vertex to investigate Rhina Gamma up close, landing a rover directly inside the swirl to take surface-level magnetic measurements. That mission has been rescheduled. Until a magnetometer is actually placed on the surface of a lunar swirl, the origin of these features will remain uncertain. The Artemis II crew saw Rhina Gamma from 4,000 miles above. They photographed it. They described it. But the mystery remains open, and it remains one of the moon's most compelling unresolved questions. I want to spend a moment on what Victor Glover described when he looked at the lunar terminator, because this observation gets almost no coverage, and it speaks directly to why human eyes in space return data that orbital cameras simply cannot. The terminator is the line on the moon's surface where sunlight ends and shadow begins. From Earth, it looks like a smooth curve sweeping across the disk. From 4,000 miles above, it looks like the edge of a world being swallowed by darkness. Glover became fixated on it. I wish I had some more time to just sit here and describe what I'm seeing, he radioed to Mission Control. But the Terminator right now is just fantastic. It is the most rugged that I have seen it from a lighting perspective. There are little islands. There are islands of terrain out there that are completely surrounded by darkness, which indicates some real variation in terrain. What he was seeing is what photographers call grazing incidence light. When the sun sits right on the horizon from the perspective of the lunar surface, it casts enormously long shadows. Every ridge, every hill, every crater rim throws a shadow that stretches across the landscape like a finger pointing away from the sun. Features that would be completely invisible in overhead illumination suddenly leap out of the surface in vivid three-dimensional relief. orbital cameras photographed the moon from directly above, with the sun illuminating the surface more or less evenly. From that perspective, small features cast short shadows that disappear into the resolution of the image. But from the Terminator angle, the long shadows expose micro-ridges, subtle fractures, ancient collapsed lava tubes, tiny elevation changes that are otherwise invisible. Glover described mountain peaks near the Terminator so bright they appeared to be covered in snow. Of course it was not snow. What he was seeing was fresh, unweathered rock, possibly plagioclase highland material, reflecting low-angle sunlight with extraordinary brilliance against the absolute black of the shadowed valleys below. The contrast was so extreme it created a visual impression that no photograph of the moon had ever produced. Koch added her own observation. She said, looking at the bright young craters from this angle, the ones whose ejecta blankets have not yet been darkened by space weathering, it really looked like a lampshade with tiny pinprick holes and a bright light shining through. They were so luminous compared to everything around them. Kelsey Young, the Artemis II lunar science lead back in Houston, responded to Glover's Terminator description with unfiltered excitement. "Oh my gosh," she radioed back. "I literally saw fist pumps in the science evaluation room. Those types of observations are things that humans are uniquely able to contribute." This is the case for sending humans. Not that human eyes are better than cameras in some absolute sense. They are not. Cameras capture more wavelengths, record data with perfect consistency, never get tired. But human eyes are connected to human brains, and human brains are pattern recognition systems refined by hundreds of millions of years of evolution. A trained observer looking at a landscape under continuously changing illumination can spot anomalies, connections, and features that a fixed camera image, regardless of resolution, will miss. More importantly, a human can react. Glover was not reading from a script when he described the Terminator. He was responding in real time to something that surprised him, and his surprise told the science team things they had not known to ask about. Before I bring this home, I want to give you the number that I think puts everything in perspective. The number that connects the visible flashes Wiseman watched, the invisible micrometeoroid flux, the engineering challenge of long-duration habitation, and the core question of what we actually understand about the environment we are planning to send people into permanently. Every single day, approximately 1.4 metric tons of meteoroid material strikes the lunar surface. That is not a typo, not a misplaced decimal. 1.4 metric tons every 24 hours, 365 days a year. Through every season and every phase cycle, regardless of whether anyone is watching, over the course of a year that is more than 500 metric tons of extraterrestrial material arriving on a world with no defense mechanism of any kind. No atmosphere to burn it up, no magnetic field to deflect the charge component, no weather to erode the craters it leaves behind. Every gram of it arrives, deposits its energy, and becomes part of the moon forever. 500 tons a year, accumulated over 4 billion years. That is the surface you are looking at when you look at the moon. Every crater, every gouge, every grain of regolith, everything down to the microscopic pits covering every rock in the Apollo sample collection is a record of that bombardment. Written in stone, preserved perfectly in an environment where nothing erases anything. The Artemis II crew watched that record being written in real time. 6 new entries in an archive 4 billion years old. 6 flashes in 60 minutes on a surface that has been hit every second of every day since before life existed on Earth to look up at it. The moon did not change on April 6, 2026. It did exactly what it has been doing for 4.5 billion years. It sat there airless and unshielded and absorbed everything the solar system threw at it. The only thing that changed was us. We finally put someone close enough, in the right geometry, at the right moment, to see what was always happening. Let me bring this home. The Artemis II mission lasted 10 days. The lunar flyby lasted 7 hours. The eclipse lasted 57 minutes. The communications blackout lasted 40. The Carol moment lasted maybe 2, and yet those moments contain more wonder, more grief, more beauty, and more truth about where we are and what we are doing than most of what fills our screens in a given month. Artemis III will land astronauts near the lunar South Pole. For the first time since December of 1972, human beings will walk on the surface of another world. They will search for water ice in the permanently shadowed craters. They will drill into the regolith. They will collect samples and set up instruments, and then, critically, they will go back inside, because the surface is not safe for long durations. Not yet. Not without the engineering solutions that are still being worked out. Artemis IV will begin construction of the Lunar Gateway Orbital Station. After that, surface habitats. After that, extended stays. After that, if the vision holds, people living on the moon the way people live in Antarctica today, in rotation, for months at a time, doing real science in a genuinely hostile environment, returning home changed, and eventually, if we get this right, something even further. The moon as a proving ground for the technologies and knowledge we will need to reach Mars, the long road that Artemis is only the beginning of. Every step in that journey depends on understanding where we are going, and what Artemis II revealed is that our picture of the lunar environment, the quiet moon, the still moon, the museum exhibit moon that stopped changing long ago, was never the moon at all. It was the limit of our instruments projected onto the sky and mistaken for reality. The moon is not quiet. It has never been quiet. It is under continuous bombardment at every scale, from microscopic dust to rocks the size of your fist, every hour of every day absorbed in silence, recorded permanently, without complaint. We did not know that viscerally, experientially, in our bodies, not until 4 people were put in a capsule and sent to a place where none of the filters we normally look through applied, and they watched it happen with their own eyes. Now we know. The question is what we do with that knowledge. If you have made it this far, I genuinely want to know what struck you most about this mission. Was it the impact flashes and what they mean for future habitats? The Carol moment? The 40 minutes of complete silence? The way the far side of the moon looks nothing like what you expected, or something else entirely? Leave it in the comments. I read all of them and I will respond to as many as I can. If this kind of deep dive is what you are here for, subscribing means you will not miss what we cover next. We do not rush these. We take our time and we go where the evidence goes. Jim Lovell said it best, from beyond the point where most of us will ever travel. Do not forget to enjoy the view.